everyone. Welcome to today's seminar on in-situ and ex-situ treatment technologies for per and polyfluoroalkyl substances, also known as PFASs. My name is Beth Mashesky. I am Senior Scientific Specialist at the Illinois Sustainable Technology Center and seminar co-organizer. Our next seminar will be on March 22nd at 12:15 p.m. It will be on managing water to increase resiliency of drained agriculture landscapes. And that will be presented by Jane Frankenberger of Purdue University. For today, I'll ask everyone to please silence electronic devices as we are recording this webinar. Also, we'll hold all questions until the end of the presentation, at which time I'll bring the microphone around so those online can hear your questions. Also, for those online, you can type in your questions at any time and we'll address those at the end as well. For those, so with that, I am very pleased to welcome today's speakers, Erika, Houtz, and Jeffrey McDonough. Erika is the PFAS analytical lead at Arcadis, and Jeff is the principal environmental engineer at Arcadis. Arcadis is a global sustainability consulting company, so please join me in welcoming them.
Thanks, Beth. Hi, this is Erika Houtz speaking first, and then I'll be followed a little bit later by my colleague, Jeff McDonough. I work for Arcadis in San Francisco, and Jeff currently works out of Portland, Maine. He and I both are pretty involved in our PFAS area of practice, which largely focuses on both site characterization and remediation. And as part of some of the work that we do at our company, we do a little bit of R&D on different PFAS treatment remedial strategies. So we'll present both some different kinds of PFAS remedial strategies that are being used by others in the industry, as well as others that we are actively exploring. So first I want to go ahead and acknowledge a couple of our funding sources of a few of the projects that we're presenting on. One is one that we've kicked off recently, funded by AFCEC. It's a project on PFAS stabilization in soils. Another is a CERTIP project with which we are teamed with Paula Edmiston at College of Worcester on development of PFAS adsorbents. And I also want to acknowledge a few of our Arcadis PFAS colleagues who have been really active in some of this work. Ian Ross, who is our global PFAS lead, Jeff Burdick, who is one of our North American co-leads, in addition to my co-presenter, Jeff McDonough. And then a few of our colleagues around the world, John Miles and Jake Hurst, are in the UK. Peter Storch is in Australia, and then Kirk Nowak is in the US. So first I wanted to kind of set the stage of where we as a consulting company are really focused on thinking about PFAS treatment. I suspect that a lot of you are kind of generally aware of PFAS as being common to a lot of consumer products. And certainly that widespread use creates sort of very diffuse low-level PFAS contamination in the environment. But we're really more focused on where we have large point sources of PFAS contamination, and in particular where they may take out, or to put it differently, where they may impact a public water supply and expose people to unacceptable levels of PFAS in drinking water. So at the top are four of the most major sources of PFAS point source contamination. The first being primary manufacturing, so where individual PFAS chemicals are manufactured. I have heard that these are usually located where there are calcium fluoride deposits, and we definitely have primary manufacturing in Minnesota, in Ohio, and in Alabama within the US. Now, what's manufactured in those locations has changed somewhat significantly over the years. Another major point source is what we usually call secondary manufacturing, where PFAS or a series of PFAS chemicals are applied to a particular kind of product. So for example, if any of you have ever flown in and out of Denver Airport, they have a really unusual building structure there where the roof is a very sturdy textile. That textile is coated with PFASs, and it's actually been linked to some environmental contamination where that PFAS-coated textile is manufactured in New England. A lot of other sources that we find, point sources of PFAS, are associated with firefighting foams. In particular, firefighting foams are used to put out fuel-based fires, or Class B fires are often called aqueous film-forming foams. And those are particularly important because PFASs occurred in those foams at relatively high concentrations, and they were released intentionally directly to the environment, either for fire training or to put out fires in an emergency. So we see that military fire training sites can be a major point source of PFASs, also airports. And then there are other sources that I would say, have less of a handle on in terms of how significant they are and how widespread they are. But certainly municipal fire training also involved the use of AFFF. Refineries have a need to keep AFFF on site to prevent emergency fires. Also large rail yards. PFASs were used in, or are currently used in metal plating and electroplating. They are used as mist-suppressants actually to prevent toxic metal fumes from exposing workers. And then also in some cases we see that wastewater treatment plants and landfills can be an important source of PFASs, particularly if they're receiving some type of PFAS manufacturing waste. And then also related to wastewater treatment plants, you could see that the application of biosolids might be another vector related to wastewater treatment plants that could result in a large localized environmental contamination of PFASs. So the PFAS class is basically two components. The first class are the perfluoroalkyl substances, essentially meaning that those compounds don't contain any carbon-hydrogen bonds, and all of the carbon-hydrogen bonds have been replaced with carbon-fluorine bonds. We generally refer to that group as the perfluoroalkyl acids because there tend to be two main types, perfluoroalkyl sulfonates and perfluoroalkyl carboxylates. There are a couple of other lesser known varieties, but those are the two big ones. So they contain a fully fluorinated carbon functional group, which can be either linear or branched, depending on how it's manufactured, and then they end in either a carboxylate or a sulfonate functional group. We refer to them typically by their anionic names because they tend to be anionic at environmental pH. Sulfonates have pKa's that are thought to be lower than 0. They're kind of challenging to measure. And then carboxylates have pKa's that are lower than 3. So generally speaking, they're pretty much anionic at environmental pH. Historically speaking, the PFAS that contained 8 carbons were manufactured in the greatest quantities. That's the C8, the octane. The third and sometimes fourth letter in the PFAS acronym usually refers to the number of carbons present in that molecule. So if we're talking about a PFHXS, we're talking about a compound that has a hexane group or a C6 group. We're talking about PFBS or PFBA. We're talking about a compound that has a C4 group for butane. All of these different perfluoroalkyl acids are, to the extent that we know at this point, completely recalcitrant to biotransformation, both via microbes and through processes that might occur in biological systems. The chain length of the compound is pretty significant. Generally speaking, as they get longer, both the sorption and bioaccumulation potential increase. So the cutoff is roughly around C8. It depends whether it's a sulfonate or a carboxylate. But compounds longer than that tend to bioaccumulate, meaning that they, or at least in the context we use them in PFASs, tend to have pretty long elimination half-lives in the body, on the order of years. So if you remove a couple of those perfluorinated carbons from the molecule, the elimination half-life in the body can be more like on the order of days. So what we've seen in manufacturing trends over the years is that there's been a real shift away from these long chain compounds to reduce the ones that are present that can bioaccumulate towards the shorter chain compounds, so that even if the persistence or the toxicity is potentially similar, the human exposure in the body will be much less. So PFOS has largely been replaced with PFBS and PFOA has been largely replaced with PFHXA. So the other half of the class, the polyfluorinated part, also contains a perfluoroalkyl group, but contains a number of carbon-hydrogen bonds as well, and generally just has a lot more structural variation than you see with the perfluoroalkyl acids, which are all essentially anions. So within the polyfluorinated part of the class, we have compounds that are volatile, such as fluorotelomere alcohols. We have compounds that have multiple charges or positive charges, which can really affect how they move in the subsurface, how they're going to stick to soils. We have some that look a lot like the PFAS, like the 6,2-fluorotelomere sulfonate compound. And the thing that's pretty significant about these polyfluorinated compounds is that unlike the PFAS, which do not transform, these compounds are susceptible to both abiotic transformation processes with, for example, hydroxyl radical, and through microbial or biological transformation processes. And generally speaking, the compounds that contain a telomer group, or that's this ethyl group that is connected to the perfluoroalkyl group, those compounds tend to biotransform to the perfluoroalkyl carboxylates. And compounds like this one over on the far right that has a sulfonamide group tends to biotransform to compounds that look like PFOS. Now, obviously, the compound that it's transforming to will not contain a longer perfluoroalkyl chain than what the precursor contained. So I did just want to quickly highlight on how we measure the precursors in particular. So the perfluoroalkyl acids are generally all pretty easy to measure on an LC tandem mass spectrometer. That's how commercial labs and academic labs typically measure those compounds. It can be harder to measure the precursors due to that wide variability in structure, and also because many of those precursor compounds, the polyfluorinated compounds, are proprietary, and you can't buy an analytical standard for them. So these are some of the techniques that have evolved to sort of capture what the precursor mass is at a site. The top one, the total oxidizable precursor assay, is something that I worked on in graduate school, and essentially we convert the precursors present in a sample to the perfluoroalkyl carboxylates, measure the sample before and after oxidation, and that increase in the perfluoroalkyl carboxylate concentration is roughly equal to the total concentration of precursors in the sample. That method is now commercially available at a number of labs around the world. The next few methods are essentially both methods that measure total organofluorine as a surrogate for total PFAS concentration, and you could represent it as like a PFOA equivalent concentration. For exact speciation of different kinds of precursors present in a sample, you could use a tool like LC quantitative time of flight. So what drives a lot of the activity around measuring and treating for PFAS is essentially what's going on in the regulatory landscape globally. So this is just sort of a snapshot of different standards we see in aqueous media, either drinking water, surface water, or groundwater. Each color on the little ring represents a different individual PFAS compound that has a regulatory value. In some cases, these are not enforceable values. They may be or just advisory values. But you can see that, for example, Texas is actually the US state that regulates the most of these compounds. US EPA has only focused on PFOS and PFOA. Countries in Europe occasionally regulate all of these compounds together as a summation. That can result in a really interesting situation where you have to develop a remedial strategy on the basis of one of the shorter chain compounds, which tend to be more recalcitrant to a lot of the different remedial technologies. Generally, the global trend is to see that more compounds are being regulated and at lower levels. Typically, we're somewhere between 10 and 100 ppt for a lot of these compounds, ppt or nanograms per liter. So when thinking about remedial treatment technologies for PFASs, there are a number of challenges that are beyond what we've experienced with other kinds of compounds that we as an industry have tried to treat in the past. That makes it an area of a lot of academic interest. There's a lot of opportunity to develop new treatment strategies. And then it's also an interesting place to work as a consultant. Sorry, let me just pull that thing off my screen. So generally speaking, chemical treatment strategies have not been very effective for PFASs. Neither the carboxylates or the sulfonates react at all with conventional AOPs, with hydroxyl radical. Under sort of limited circumstances, we've seen persulfate-related radicals be effective at treating the carboxylates. And then because these molecules are already so oxidized, sometimes there's potentially a way to work in an advanced reduction process to treat these compounds chemically, but generally speaking, these are not very viable in the field scale. At the field scale, there's a lot of different scavengers that will react with electrons and other reducing agents before the PFASs would. Biologically speaking, PFAS are completely resistant to biodegradation. We have seen partial defluorination of polyfluorinated compounds through microbial processes. You maybe see 2 or 3 carbons defluorinated. That's of use when we're talking about this bioaccumulation concept, and if you can partially defluorinate a C8 precursor to a C6, that can be useful because it then becomes a less bioaccumulative terminal compound. In terms of physical processes, so different separation techniques or efforts to kind of bind up PFASs. This has been kind of the sweet spot of remediation for PFASs thus far, but not every type of physical process works very well for the whole range of the class. Another option within the space is incineration, but that's expensive and generally speaking unsustainable. So I wanted to give you kind of an overview of different kinds of treatment technologies for both water, and the next slide will be soil, kind of on the range of whether they're experimental or mature or not particularly viable, even if they could in theory work, versus feasible. So the technologies that are surrounded by a blue box represent destructive technologies, and the ones that are surrounded by a black box represent adsorptive or separation technologies. So over on the very mature and feasible side, we have activated carbon. That's the most common thing used to treat for PFOS and PFOA, at least in an ex-situ water treatment type of strategy. Ion exchange is also used at some sites, particularly for polishing. We also see that ozofractionation is a pretty successful type of separation technology. It's not mature in the same way that it's used widespread as activated carbon and ion exchange, but we'll show you an example of where we've used this in a full-scale system. Kind of in the middle, things that are potentially practical and somewhat mature, we have Sonolysis and electrochemistry as different destructive treatment technologies, but they often require a really concentrated waste stream. So when we're potentially dealing with a water supply that has 100 parts per trillion PFOS, PFOA, and we want to bring it down to say 35, that's not an ideal candidate for a destructive treatment technology like one of those. And then for soil and sediment, we've got fewer options on the table currently. Again, we've got both sort of the separation-based technologies and the destruction-based technologies. Over at the top, soil stabilization is something that we've been exploring. This has been used for a lot of other kinds of contaminants, historically speaking, and it's a way to essentially immobilize PFASs rather than destroying them, but it can still, result in that effect of protecting a water supply that we're usually interested in. There's also sort of less mature ex-situ thermal strategies that involve sort of thermal desorption and then destruction in a vapor phase. That's something that we've been considering using as a company. And then soil washing is another thing that hasn't been used much for PFASs, but has been used for other kinds of chemicals. It's sort of like what it sounds like, where you apply some type of a solvent or another pH adjusted type of reagent to a bunch of soil, and you try to remove the PFASs through a separation process. And then often incineration is still used to treat PFASs in soil, just because of sort of the state of maturity of some of these other technologies. CERDIP is one of the main funders of research around PFAS remediation. CERDIP is associated with DoD, and the main reason why they've taken such an interest in PFAS is because they have a lot of firefighting foam related contamination at different installations. So some of you may currently work on CERDIP funded projects, but I just wanted to highlight what they've been funding in recent years in 2018. And I think that gives you an idea of what people consider viable in the PFAS treatment and remediation space. So of the 11 or 12 projects that were funded for fiscal year 2018, a total of 7 of them had to do with either novel adsorbents. There's some promising cyclodextrin type sorbents, another type called Purasorb that we'll be presenting on. And then also sorbents related to the ion exchange and regenerating those so they can be reused. Less of an emphasis on destructive technologies. So 1 project on UV-induced defluorination, and then 3 on electrochemical-based destruction. And then finally, before we move into a more detailed discussion of the treatment technologies, just want to emphasize that a really important part of any kind of remedial strategy implementation is locating where exactly the PFAS mass is important. Locating where the PFAS mass is a very important element of the strategy. And a lot of times you need to think about what was the release mechanism. So if it was a surface release, you may have a lot of PFASs situated in your unsaturated soil zone. That can then impact the groundwater column through infiltration. If you have an aerial deposition type of release or discharge from treatment plants, that could impact more easily a surface water type of source. And then one thing I wanted to point out with these soil and groundwater depth profiles, this was a site that we did a pretty detailed investigation at, and we saw that while our main concern was groundwater moving offsite with PFASs and impacting a drinking water supply, that most of the PFASs were actually hung up in the top of the superficial soil. 98% of the mass was actually in the top 2 meters of the site. So even though our main focus was kind of dealing with the groundwater, you have to consider what's going on with the surface soil, perhaps as a way to get to the groundwater treatment strategy. So every site's a little different. Depth of groundwater matters quite a lot. What the geology at the site is matters. And understanding those kinds of things can really help tailor the right strategy for PFAS treatment. So we're going to focus on 3 different categories of PFAS treatment. The first being adsorption separation, second being fixation, and the third being destruction. I'm going to talk to adsorption and separation, and Jeff will talk to fixation and destruction. So we'll start with the activated carbon, which is the most popular type of ex-situ treatment strategy to use for PFASs. It's effective for surface water, groundwater, also drinking water. The point of entry systems are when you apply it in someone's residence. And we know that it works really well for removing PFOS and PFOA. You can get greater than 90% removal even at very low concentrations, and with a 7 to 15 minute empty bed contact time. You can potentially reactivate GAC. You can return it to the manufacturer. They can regenerate it at a high temperature, and then you can reuse it, which can sort of improve the overall sustainability and cost. Essentially, it's pretty easy to use, and so it's an easy de facto choice. Some of the limitations are that it doesn't perform as well for some of the short chain PFASs. Sorry, seems like my cursor was going. It doesn't perform as well for some of the short chain PFASs, and then with the precursors, it's sort of even less well understood with how well GAC is going to do. So in terms of trying to select a remedial strategy that's comprehensive, GAC does have some limitations. And then there's also competition for sorption sites with natural organic matter, other kinds of co-contaminants. So really the focus when trying to design an activated carbon remedial strategy right now is on different ways to optimize the strategy. So this is from a publication that came out in 2017, and it essentially highlights some of these limitations on GAC that we were just discussing. And so this is the performance, or sorry, these are log KD values for sorption on a coal-based GAC over here of different kinds of individual PFASs. The starred PFASs are the ones that contain 6 perfluoroalkyl carbons, and then within each different color, it goes from short to long chain. So we see, generally speaking, that the KD values go up about a half a log unit per, or a quarter of a log unit per carbon. So we see, greater effectiveness for the long chain carbons. We also generally see that for the same perfluoroalkyl chain length, the precursors do tend to sorb a little bit better on this particular type of carbon than the carboxylates and the sulfonates. And so this is from a full-scale system treating drinking water that contained PFBA, PFOA, and PFOS. PFBA, again, being that short chain compound, that one is in the squares. So we're looking at concentration in the effluent over the influent concentration. What we see with PFBA, sorry, this is over a 5-year period, PFBA starts to break through first, which is what we would expect. We actually see it breaking through at a concentration higher than its original concentration in the influent. That could be due to transformation or precursors, but usually this is just a case of competitive sorption effects, where not only is PFBA now breaking through, but it's desorbing in favor of sorbing some of the longer chain compounds. And you can see noticeable effects from when you replace the lead and lag GAC vessels. So down here, when you replace the lead vessel, which is supposed to capture the bulk of the mass, we see the PFOA and PFOS concentrations drop back down again. We did not see that with PFBA because it was already saturated through the lag vessel. When you replace both vessels, you get all the concentrations dropping down again, and your performance kind of picks up just like where it started. So different things that can be used to optimize how you think about the sustainability of a GAC treatment process. Really, it has to do a lot with how you size the vessels and how often you're doing operation and maintenance and change outs. Also the type of GAC that you select. So there's different kinds of granular activated carbon available. A bunch of them are coal-based, some of them are coconut shell-based. Generally speaking, we see that mesoporous GAC performs better for PFASs than microporous GAC, so that can be kind of a decision point to find a more effective strategy. Also, sometimes it's really sort of simple things. You can purchase a subbituminous GAC. We see on the right that bituminous and subbituminous GAC perform pretty similarly in terms of breakthrough before they need to be replaced, but subbituminous may just be more cost effective because it's less dense and usually buy GAC on a weight basis. Another huge factor for increasing your GAC longevity is pre-treating, particularly for natural organic matter or total organic carbon that is found to co-occur in natural waters or other things you might be treating. Co-contaminants could be another issue. So you can see on the right, for a very similar PFOA influent concentration and an order of magnitude difference in total organic carbon breakthrough was much faster for PFOA in the higher TOC water. So thinking about how to control TOC, going into one of these systems is helpful. You can do that through pH adjustment by increasing the pH. TOC will be less responsive to sticking to the GAC, but that won't actually affect the PFAS. Additionally, you could pre-treat through flocculation or through some type of advanced oxidation process, which would be effective towards TOC and co-contaminants, but probably wouldn't really impact your PFAS. Another thing you can do to optimize your use of activated carbon, if you have a really highly concentrated influent stream, you can use a PFAS-specific flocculation and precipitation technique to bring down the concentration of PFAS before hitting the GAC. The problem is then that you have kind of a secondary wastewater or waste stream, and that really only works if you have a very concentrated sample, like more than 20 parts per billion, which is higher than what you would see at most sites where we're kind of dealing with this. So it's just sort of thinking about what your treatment train looks like, how to extend the longevity of what you've chosen. In this case, we've been focusing on activated carbon. Another thing that's really is just more of a practical, functional type of idea. If you're focused on controlling costs for treating for these compounds, sometimes simply by investing in a higher capital cost, so a 10,000 pound set of GAC vessels versus 2,000 pounds, you can have a kind of a similar lifetime O&M cost, which can be useful, particularly if you're trying to deal with a system that's in a remote location or where it's difficult to mobilize people to get to. It can be useful to invest more upfront in a larger system that requires less frequent change-outs. So soil washing is another separation technique used for soil treatment. Generally speaking, this is only something you would want to deploy if you had relatively large quantity of soil you wanted to treat. There's different things you can use to do soil washing. You can use a surfactant that could potentially desorb PFASs. You could use a solvent such as methanol. Again, there's sort of variability in how different PFASs sorb and desorb, and so kind of getting everything at once can be a little bit of a challenge. And then you do have a waste stream that requires treatment after that, but that can be maybe a more concentrated waste stream, which is often easier to treat from a destructive point of view than low concentration waste streams. Another type of separation technology that's used is typically anion exchange. That's because PFASs are typically anions. Even though, the technology sounds like it's all about ionic effects, actually still the hydrophobic interactions matter quite a lot. So the longer chain compounds tend to perform a little better with removal by anion exchange than the short chain ones. Although this can be a more effective way to treat ionic PFASs that are shorter through that additional ionic interaction. And so typically where we're seeing anion exchange resins used is sort of a polishing step after GAC treatment. Anion exchange resins tend to be quite a bit more expensive than something like activated carbon. So they can be used to get down to really low treatment targets that some people are trying to achieve. They also have smaller equipment footprints, lower empty bed contact times, so they can be a little more versatile in that way to deploy as a full-scale system. But similar to GAC, sometimes you have to think about optimization, and depending on what other kinds of anions are present in your source water, that may be a limitation towards being able to use different kinds of anion exchange resins. One thing that appeals to a lot of people about using anion exchange resins versus something like GAC is that if you can desorb the PFASs using a solvent or a pH adjustment effect, you can really extend the longevity of the resins for lifetime of treatment. But again, you have a waste stream you have to treat. So as I highlighted with some of those CERTIP-funded projects recently, there's been a big focus on sort of new specialized sorbents for the removal of PFAS. This is an example of adsorption isotherms for a product called PureSorb. And it's made out of an organo-silica-coated sand. What's useful about some of these more novel sorbents is that sometimes they perform really well for some of the compounds that we're struggling to treat, like the short chain ones. So the sorption isotherm on the right is for PFBA, and with the exception of sort of this errant data point around 1,000 ppb, we see actually much better removal of PFBA with this PureSorb product than we did for PFOA and PFOS. So it's useful to kind of have a toolbox of different sorbents that can target different PFASs that can either be used as in series or potentially that are a good catch-all for all of them. So you can also modify this material with different sort of fluorinated functional groups that can improve its affinity for PFASs. And this is a focus of a sort of funded project that we're working on now, trying to improve this sorbent for removal of PFASs. And part of that too is also focusing on regeneration potential of this sorbent. That's an area of really active research, just trying to understand how you can improve the longevity of these different kinds of materials. Another separation technology that we've used predominantly in Australia is a concept called ozofractionation. We've been using it with wastewater, so really high organic content and a lot of other co-contaminants. So ozofractionation was originally not designed for PFASs. Was designed for other kinds of contaminants such as hydrocarbons that can actually break down with ozone. But the nice thing about using an ozofractionation is that by exposing a waste stream to ozone, you get both destruction of your co-contaminants, and then you get a bubbling effect, which works really well to separate out PFASs that tend to be surfactants. By separating out surfactants in just sort of the air phase or the bubble phase, you create a concentrated waste stream of PFASs that you can then treat separately. So the feed water goes through 3 different ozofractionation tanks. Each time the waste stream comes out at the top, the kind of the airy waste stream, and then the treated stream, which goes through each of these different fractionators, is also finally treated with an adsorbent to get down to really low levels of PFASs to meet discharge requirements. So you end up with a concentrate, some spent media, and then a foamy sludge on the top. Sorry, that's the concentrate. Then also your final treated water. So this is kind of what one of these systems looks like on the right. This is from the field scale application that we use this for in Australia. So we had different kinds of waste streams. In the pilot application, we were working with a total PFAS concentration of around 4,000 micrograms per liter, and we were aiming for a targeted discharge value of less than a microgram per liter. So we kind of got this to work in partnership with a company called Avacra at the lab scale, and then brought it to the field scale to treat 3.6 million gallons of water at this particular site. So this was the sort of removal that we achieved. In the ozofractionation stages, we were able to achieve between 95 and 98% removal of a lot of our target compounds, PFOS, PFOA, 6,2-FTS. Ozofractionation did not work as well for the short chain compounds. You actually see net production, and this is because the ozone converts some of the precursors in the process to these short chain compounds. But by applying an adsorbent like Ozorb or PureSorb in the polishing stage, you can get additional removal to get much closer to your target discharge value. So in total, we saw 99.6% removal of total PFAS as measured by one of those alternative techniques, top assay. In the ozofractionation stage, an additional 89.6% removal from that adsorbent stage. And so we were able to take the influent to effluent treated water from about 4,000 micrograms per liter to about 2. And this was in the pilot scale. And then with the full scale water, which was not quite as contaminated as that pilot scale water, we were able to get below our discharge limit of 1 microgram per liter or 1 part per billion. We replaced the polishing step in the full scale system with nano-filtration just to ensure that we could meet our desired discharge limits. And so we ended up with a concentrated waste stream that was about 0.5% to 2% of the treated water volume. So by really concentrating up those PFASs into a much smaller scale waste stream, that makes it more viable to start using some of the more expensive destructive techniques that really work much better cost-wise at a more concentrated level. Okay, and so next I'm going to pass this to Jeff.
Hey, can you guys hear me okay?
Yep, we can hear you.
All right, cool. So I'm going to talk about fixation and destruction-based technologies for PFAS. Now, a lot of the stuff that I'm going to present here is conceptual, and that's why we're evaluating it, because there hasn't been very much action by the industry to actively remediate these compounds just yet. There's a lot of what Erika talked about are stopgap measures that have been put in place to address immediate concerns to public water supplies. The next section of this talk is going to focus a little bit more on what people are thinking about what to do about this problem. So right now we're kind of just catching it and building some research up as to what we can do to address it. And the first technology that I'm going to talk through is fixation. Please advance. Erika, can you help me advance that?
Yeah, I think you should have control now.
Okay.
Sorry about that.
All right. So I just wanted to put up a little bit of a picture to show you what I mean when I say soil stabilization, because that's the method by which we can distribute our fixants. Fixation is basically the process of creating really low soluble and low leachable concentrations of contaminants through adsorption with different chemical reagents. And those chemical reagents are typically insoluble. You're not going to be able to inject them. And even if you do inject them, the certainty with which you distribute them throughout an area may be less, because it's going to primarily distribute along higher hydraulic conductivity seams. So one of the ways to distribute them pretty effectively is to really destroy the soil structure with in situ mixing, or what's been called soil stabilization, using a variety of tools. There's all sorts of different technologies out there, variations of augers, variations of excavator arm attachments and things like that, that we can destroy the soil structure and ensure that we can deliver the reagent throughout. I have in there potentially solidification as well. Some of the areas that we're looking at treating for this are abandoned fire training areas that really don't have much traffic. It's not necessarily required that the soil be immediately returned to load-bearing capacity. So the solidifying agent that might be like a Portland cement to give you an unconfined compressive strength to immediately use the soil after treatment, that may or may not be necessary. And it's important because some of the research that we're doing is looking at how that the aluminum silicate chemistry associated with Portland cement, how that influences some of the fixation strategies. So the basis for fixation came from a gentleman by the name of Peter Storch, a colleague of ours out in Australia, who started playing around with different fixants shown on the right, of a proprietary blend of aluminum hydroxide and granular activated carbon, pyrolyzed cellulose, and modified clay, all of which are sold commercially under different proprietary trade names. But essentially what the mechanisms are either electrostatic or hydrophobic adsorption of the PFAS from water. So we ran some studies, or Peter ran some studies, in which he varied the dose of these different fixants from 5 to 25% by weight, shown on the x-axis, and then looked at the resultant sum of PFAS in microcosm studies in bottles. So we had a control concentration of just about 2,000 micrograms per liter. The raw water was about 1,500 micrograms per liter. And after the fixant was mixed with the water and shaken up and incubated for a certain amount of time, you can see on the log scale of the y-axis that there were orders of magnitude reduction in the concentration of PFAS in the water. So what that means is that from a leachate perspective, if these fixants were mixed into an aquifer, into a soil water slurry, we would effectively mitigate the leachate from the soil to the water. So you're not destroying them, you're not removing them, you're locking them up in place and preventing them from getting into a groundwater, which then becomes a mobile problem. So it's about managing the risk and taking the receptor out of the equation, because people aren't interacting with these soils. They're restricted under either institutional controls, or a lot of what our clients are considering doing is using soil stabilization in a fire training area and then building another fire training area on top of it, and using a different variety of foams, ones that don't necessarily have the fluorosurfactant. But the real question is, how effective will this be long term? I mean, if you talk to the vendors who provide these materials, they're advertising 10,000 years of longevity, and they're doing it by simulating leachate testing. Now, a lot of the commercial leachate testing, the synthetic precipitation leachate procedure and the toxic characteristic leaching procedures, SPLP and TCLP, they were designed historically for metals leaching from landfills. So they looked at an acidic-based leachate. Well, PFAS has turned everything on its head from a remediation perspective, and PFAS are actually more adsorptive, or the ones that we're concerned with at the moment and will be for a while, the perfluoroalkyl acids that Erika was discussing, they tend to be more adsorptive under acidic conditions because you have more positively surface charges in situ, and they're anionic. So running your simulated leach 10,000 times with acidic material doesn't necessarily give you a look at the worst case scenario. So one thing that we're evaluating in a field scale comparison, which is funded by the US Air Force under a broad agency announcement that we were awarded in 2017, is we're basically going to mix up 4 10 by 10 plots in a contaminated area impacted with PFAS, and look at a time series comparison of the permanence of fixation. So typically you don't think of soil stabilization with time series data. It's generally set up that you would demonstrate viability in bench and column studies. You would establish a technical quality control and assurance plan to make sure that the field scale mix is identical to what you did in the laboratory, and then that's your proof of concept, and you don't further sample the monolith. That's typically the way that ISS systems work. You may monitor groundwater for subsequent leachate for a while, but you generally don't go back into the monolith to disturb it. We're going to do that because in this instance, it's not a destructive-based treatment. We're trying to see if we've mitigated leachate. So we're going to mix in the variety of stabilizing agents, whichever ones we see fit from a laboratory bench scale, and then we're going to run over 3 years 4 sampling events, so generally annually sampling plus a baseline event. We're going to look at PFAS in soil and groundwater. We're going to use Erika's method of the total oxidizable precursor assay to look at how precursors are influenced with the adsorption. Organic carbon's a big thing when we're talking about adsorption, and it's competition with the fixants that we're mixing in. Target analyte list metals, grain size from a geotechnical perspective, moisture content from a geotechnical perspective, and other major anions and cations in groundwater that can influence the adsorptive nature and fixation ability of the fixants that we're mixing. And we're going to use a slightly different version. So we're not going to use TCLIP or SPLP. We're going to use a sequential leaching test called LEAF, which is method 1315. It was developed with Arcadis and Vanderbilt University and has since been commercialized. But it uses a circumneutral leachate extractant to run intact monoliths through a series of leaching. It's the most accurate way to represent what the field scale will actually be subjected to over time, and does it at circumneutral pH. So it's giving us a worst case scenario from a PFAS leachate perspective. I'm going to end here with some discussion on destruction. Now, the destruction, we start to get into somewhat more science fiction-y type stuff, you know, technologies that may have been evaluated for hydrocarbons or CVOCs back in the 90s and 2000s, and people kind of laughed them off just because of the energy intensive nature of them. So I'm going to talk a little bit about them, but the first one that I want to talk about is one that everyone kind of says, well, why doesn't ISCO work? Why doesn't chemical oxidation work, right? I mean, ISCO is the big hammer. It's one of the most powerful chemistries that we can generate in bottles and in field scale. There's minimal promise with ISCO. I jokingly refer to it as NISCO or ISNO because it's not applicable, and I'll explain why in a couple minutes. But there's some literature that would suggest under pretty extreme conditions of generating advanced oxidative processes, those radicals that perpetuate radical mechanisms may be effective on the perfluoroalkyl carboxylic acids that Erika was talking about earlier, but maybe not so much on the sulfonates. However, some of the aggressive chemistry that would be necessary to destroy the PFCAs occurs, or it causes acidic pH. And that acidic pH can start to infringe upon the acid dissociation constant of the perfluorocarboxylic acid. So once you get down around pH 3.5, you can start to protonate some of the perfluorocarboxylic acids, and that increases their volatility. So are you really destroying them, or are you driving the acidic conditions so low that you're driving them off via volatility? I think that's an area of study in research in the literature at the moment. There's certainly a potential to transform precursors to perfluoroalkyl acids per ISCO. I mean, that's the whole concept behind the top assay. And there may be some synergistic effects of combining both AOP and ARP at the same time, but Erika highlighted that a lot of those reducing radicals that would be doing the brunt of the work are very, very easily scavenged and difficult to perpetuate in a natural system. So when we evaluate a chemical treatment strategy, we typically look at thermodynamics and kinetics. So the thermodynamics are kind of listed there, the typical Gibbs free energy evaluation or electrochemical potential of what we would need to oxidize or destroy the fluorine bond. And it's very high compared to what we can achieve from the hydroxyl radical, the aqueated electron, and the sulfate radical. So just from a thermodynamics perspective, we're a little bit behind the 8 ball. And then if you also look at the kinetic side of it, well, the bottom kinetic on the order of 10 to the 10, second order on the order of 10 to the 10, 10 to the 6 to 10 to the 10, that's how all of these radicals react with co-contaminants or other geochemical scavengers. And the rate at which it reacts with PFOA from this specific study in 2009 is on the order of 10 to the 5. So we're already behind the 8 ball from an energy perspective, and then there's stuff that can consume it much more quickly than the radicals will react with the carboxylic acid. So it's a double whammy of difficulty to overcome from a chemical perspective. That's why chemistry is pretty difficult to destroy these compounds. So we go to the outreach program and start looking at what else there is. Well, Sonolysis is something that's pretty promising in the literature. Sonolysis, if you're not familiar with it, the brief definition of it is passing sound waves through water to facilitate microbubbles, and then through the successive frequency of those sound waves passing through the water, the microbubbles are both stretched and compressed at an extremely high frequency such that the bubbles begin to collapse, and that's called cavitation. When that happens under normal pressure conditions, the temperature can go significantly higher, and as high as 5,000 degrees Kelvin, and that can facilitate either thermal degradation or pyrolysis of the PFAS. And as Erika pointed out with the ozofractionation technology, the fluorosurfactant nature of these compounds, they're drawn or partitioned to the surface of bubbles. So when we're generating super high temperatures in proximity to bubbles, and we have contaminants that like to partition to bubbles, we can get thermal destruction just via ultrasound application. The benefits, it's been demonstrated in the literature, and there are some options of green energy sources to power these units. So the energy, I'm going to talk about energy in a second, that can be a significant limitation associated with Sonolysis when you try to apply it to field scale. But in the absence of chemical destruction and in the absence of biological destruction, this could be an option for treating concentrated wastes where we can control residence times and we can control circulation. So some of the limitations, typically the sulfonate is a little bit more challenging from a rate constant perspective. That means it's going to require a little bit more time and energy. The effectiveness of Sonolysis in the literature hasn't really been demonstrated down to the levels that we would need it to be from a health advisory level perspective, like the tens of parts per trillion. But if used in a concentrated waste treatment perspective with circulation to reconcentrate, that's its sweet spot. It's not, like Erika had said earlier, we're not going to apply a Sonolysis unit to a 1 million gallon per day system. That doesn't make sense from an economics or feasibility perspective. But if we can concentrate and sweeten the load down to a point where we can control the circulation rate, then there's some viability. But the energy consumption it's a lot, right? I mean, look at the graph on the right there. That assumes about 0.12 per kilowatt hour and an operation of about 10 hours per day. And what we're seeing from application energy and energy consumption from Sonolysis is that it's about 0.3 kilowatt hours per liter treated. So if you've got systems that anywhere from 0.05 all the way to 500 gallons per minute, you can see that's a log scale of those costs from 10 hours per day. That's a lot of money to run electrical for a Sonolysis system. So the focus again on this technology is concentrated volumes, or really high concentrated low volume treatment. The next one I want to talk about is electrochemical treatment. This is one that's being commercialized. There's a few people who provide these anodes, the reactive anodes, but essentially electrochemical oxidation is the direct electron transfer of the solvated electron essentially from the surface of the anode to the PFAS. So it's an advanced reducing process, but we don't really have the ability for the solvated electron to be scavenged because it's being directly passed to the PFAS that has adsorbed or partitioned onto the surface of the anode. So it's a direct electron transfer. And the effectiveness has been demonstrated pretty widely in the literature. There's a bunch of publications since about 2015 until present that have started to evaluate electrochemical treatment. And I'm specifically saying electrochemical treatment and not electrochemical oxidation, because there's been some research to show that the hydroxyl radical that's generated when electricity is passed through water and facilitates the disproportionation of water into solvated electrons and hydroxyl radicals and hydrogen radicals and all the great stuff that we get when we separate the water molecule, those oxidative mechanisms are not as effective as the reducing mechanism, the direct electron transfer. So I specifically call this electrochemical treatment. The plot on the right shows some effectiveness, and what it gets at is the sweet spot for this technology. It just like Sonolysis, is for high concentration, low volume waste. And you can see from the power, so the power generation, or I'm sorry, the used power is presented on the x-axis, and the resultant decrease in PFAS, sum of PFAS, is shown on the y-axis. And in order to go from about 33 parts per billion, or 33,000 parts per trillion, to 4, that extra 1% of power is basically doubling the power demand. So 0.26 kilowatt hours per liter treated versus 0.15 kilowatt hours per liter treated. So what that means is that putting that extra bit of energy in to get that further along treatment, the juice is not worth the squeeze. It's better to treat down to 33,000 and then reconcentrate back to over a ppm and treat it again. That's what this plot is trying to show. So there's confirmation in the literature that it works, but very much like Sonolysis, its sweet spot is on high concentration, low volume waste. Now, unlike Sonolysis, one of the limitations associated with electrochemical is that we do generate those hydroxyl radicals and all the other stuff that goes along with advanced oxidating processes. So if you're treating a waste that has chloride or bromide, you have the potential to generate perchlorate or bromate. And those are secondary water quality compounds that have regulatory limits. And those are things that basically need to be treated. So the best practice for PFAS treatment is treatment train. If you do go the way of electrochemical treatment, there's resins and anaerobic digesters to handle some of the products that you'll generate, but that's cost and consideration that needs to be included. Last thing I'll say on the electrochemical treatment is that the acidity around the anode provides an adsorption site for, particularly for PFAS, but also for other perfluoroalkyl acids. That gets back to the discussion on the fixation that when you have anions and positively charged anionic surface, you can get adsorption. There's been some publications to suggest that, well, the fluoride mass balance, maybe that didn't add up perfectly from a treatment perspective. So could it have been some adsorption of the PFAS to the electrode? So in summary, to wrap this up, Erika did a wonderful job explaining the recalcitrant nature of PFAS, the precursor loading. It's a very complicated issue, and developing a remedial strategy that's all-inclusive is probably not going to happen. The best practice right now is treatment train, and it's treatment train because we're catching it with adsorption and trying to find the best way to manage the adsorbents. But the concept is take the high volume, low concentration waste stream and change it into a low volume, high concentrated waste stream, and then focus your energy on a lower volume at a rate that you can control. But everything is very much treatment train, and optimizing GAC or optimizing ion exchange, whatever we're doing, is very much focused on multiple components of a treatment system. The destructive techniques are very much in development. There's ones being generated all the time. Some great work at the Clarkson University on plasma generation that the U.S. Air Force is teaming on them with. And it's promising, but when you start talking about plasma and bringing electrochemical treatment or Sonolysis into the field scale, there's going to be some considerable scale-up issues that we're going to have to wrestle with. The one slide that Erika presented about life cycle costs and evaluating that from some adsorption-based remedies, it's very important to understand that the quick fix IRMs that we're putting out, they come with a life cycle price tag. So it does make sense to run the engineering cost evaluation up front to find out what that's going to look like. And then lastly, it's behooving upon all of us in this industry to not abandon the institutional knowledge that we've gained over 40-some years of remediation experience. If we're doing groundwater extraction, we don't want to go back to pump and treats, failed pump and treat remedies with GAC adsorption that doesn't work. We've got many new ways of implementing in situ techniques. We've got a lot of great ways to optimize GAC, things that we've learned along the way. So I'd encourage all of you and anyone else who's listening to focus on not abandoning the institutional knowledge that we have as an industry. Thank you very much for the time to present to you guys today.
Thank you. Do we have any questions from our audience here? Yep.
So I've got a question related to ultimate destruction via incineration. So in the end, if you incinerate an activated carbon that has the compounds absorbed to it, what's the ultimate fate of the fluoride, and is that acceptable environmentally, or does it cause another problem downstream? And it would seem like in the end, even for the destructive techniques that you mentioned at the end, you're either going to end up with fluoride in the water or fluoride in the air, or some combination of the both. And so I just wondered what is a truly destructive technique or an ultimate outcome that is acceptable for the material?
It's a great question. I can start, and Erika can answer anything else that I miss. So I'll handle the first part about incineration of activated carbon. Activated carbon was never necessarily be incinerated. The reactivation process occurs at a temperature that's commensurate with PFAS destruction, but the GAC doesn't get destroyed. You might lose 15% to char, but the reactivation process is at a high enough temperature that you'll separate and destroy the PFAS and be able to reuse the activated carbon. Now, one thing that we're hearing from vendors, and it's a great question about the fluoride, is that it creates a hydrofluoric acid that can be pretty damaging to some of the ceramic kilns that they use to reactivate this carbon. So they've been using different scrubbers and different vapor treatment techniques to basically neutralize down and get the fluoride just as aqueous fluoride. There are regulatory limits, I believe, for fluoride, but the ultimate endpoint of PFAS destruction is the mineralization of the carbon. Or generation of sulfate or mineralization of the carbon, such that we're generating CO2, sulfate, and fluoride, which all have very, very different toxicological profiles than the PFAS themselves.
Yeah, I think Jeff covered that pretty well. There are certain kinds of, I believe I've heard ceramic kilns that are able to kind of lock in the hydrofluoric acid as calcium fluoride. I'm not totally sure how that process works, but the HF generation is a pretty big concern when you're generating or when you're incinerating really concentrated PFAS waste. But yeah, in terms of thinking about the fluoride that's generated with some of these, that's been less of a concern as far as I can see as a potential byproduct.
And some of the HF that's generated from an aqueous destruction, like with Electrochem or Sonolysis, is managed via pH buffer. So keeping the pH within a range where you're not going to speciate the hydrofluoric acid, because its pKa is below 4. I think it's like 3.3 or something.
Okay, we have another question here.
Hi, Eric. You mentioned several methods for the PFAS treatment. What's your perspective about phytoremediation to treat the in-situ for the PFAS?
Yeah, so we have seen certain kinds of crops can concentrate PFASs. There's not really, I think, excellent data on that so far, but I guess we're generally not considering it as a particularly viable treatment strategy. I mean, unlike for volatile compounds, we're not really assuming that we're going to convert a water problem into, a diffuse air quality issue. That's kind of a non-issue, I guess, by virtue of the concentrations being released. So we are expecting it will just concentrate to an extent in the biomass, but whether we would both get enough concentration to achieve clean enough water for whatever the particular cleanup guideline would be, that's I think not very well understood. Perhaps people are doing research on that now, but we do think about kind of related phyto concepts in terms of, are people being exposed through the crops they're eating if they're harvesting crops in an area with PFAS groundwater. So certainly we know that can be an issue, that there's some concentration. Whether it's enough is really, I think, kind of an open question, where we would then harvest the plants and incinerate them.
We have one more question here.
Yeah, that leads into the fact that we have a Chanute Air Force Base that's closed down here. That was formerly one of the major firefighting areas for the Air Force, and there's known PFAS concentrations there, and they were actually growing crops there. Now, I've wondered about the plumes. They claim they know where the plumes are and that they don't move, but are PFAS, do they ride on top of water? So like if there's flooding in an area, can the flooding move the PFAS to new areas, or do they tend to stay in place? Because they tell me that the plumes don't move, and I find that hard to believe.
That's It's a strange way to, I feel like a plume sort of inherently assumes some amount of movement has already happened. PFASs are actually pretty mobile compared to a lot of other compounds that we've focused on historically. They do sorb somewhat to soils, both through mainly hydrophobic processes, but also ionic processes in some cases. But they don't have very high log KOCs. Like PFOA and PFOS have log KOCs of 2 and 2.5 respectively, I believe. So yeah, and surface water migration is a transport pathway. Infiltration of rainfall into soils does result in percolation of these compounds downwards. Do you want to add something, Jeff?
Yeah, just a little. So I wonder if the motivation behind that statement that they don't move. Erika is absolutely right. These things are very soluble, and as the chain length decreases, they become near miscible in water. But there is some retardation in situ. There's she was talking electrostatic. Just from the anionic nature, but then also hydrophobic. There is some retardation, but they do move. We've seen plumes as long as miles emanating from a known point source. So the question about does it ride on the surface of the water, is that, so they're not separate phase. They are going to be completely dissolved in water, and they'll move with the groundwater where it's moving. Okay, so the lithology sometimes can influence how fast something moves as well. So if you're in very dense clays with low permeability and low hydraulic conductivity, then that in and of itself can sequester a plume. But if you do have reasonable gradients and reasonable permeability, we would expect these to move somewhat similar to chlorinateds, like chlorinated volatile organic compounds, but without the destructive attenuation. So chlorinated solvents can be consumed biologically, abiotically, they can volatilize. The PFAS aren't going to do those types of mechanisms, so we would expect longer plumes from the PFAS perspective.
That's very helpful, thank you. I had a second question. We also have a electroplating company, Flexingate, that has a permit to discharge into our sewage system. And the sewage system, I don't think, uses any sophisticated thing. I mean, they have anaerobic digesters, aerobic digesters, but they just discharge the water into the same drainage ditch that they got it from for after it's been treated. And then most of the sludge is termed biosolids and goes out to farmers' fields. And I'm wondering, should we be worried about that more than we are here locally?
It's hard to say. Whether all electroplating operations use PFAS as mistsuppressants is not well understood. We do know it can be a fairly common practice, but depending on how big of a source that particular discharger would be to the local wastewater treatment plant, there might be significant enough dilution that it wouldn't create highly concentrated biosolids. It's sort of hard to know without testing it.
Okay, thanks. We got one more if there's time.
Sure.
So I had a question on the Sonolysis. You mentioned the high energy inputs. I was curious if you separated the energy required for creating the bubbles via via ultrasound versus the actual destructive cavitations that occur, on the surface of the bubbles, because I've had some experience where actually most of the energy goes into creating the bubbles, and you can create the bubbles potentially some other ways that, by many orders of magnitude could lower the total energy requirement for that process. So just curious if you've tried to separate those two.
That's a great point. Yeah, there's a host of optimization techniques for Sonolysis that we're evaluating, and I believe some of the work that University of Arizona has done with Pierre and Manish were the ones that kind of worked on some of that infused bubbles to decrease the energy usage. So we're playing around with it. The other side of it is that the bubbles that you generate, the surface area of the bubble that you generate, is equally as important as the energy that's released when it collapses. Because most of the Sonolysis that's been implemented in food services or abrasion resistance or cleaning, micro cleaning, and all that sort of stuff has used lower frequencies for PFAS destruction. I'm sorry, for bubble generation and stuff like that. And those generate larger bubbles with even more energy. So I do know that there's been some focus on energy reductions at lower frequencies with bubbles, with adding bubbles. That's a great point.
Let's take a question from online now.
So we have on this one, pump and treat will not restore aquifers to point of use treatment using GAC and or resins to become widely applied at many impacted water supply systems. Do you see the point of use treatment becoming the main approach?
As an interim action, yeah, right. I mean, that seems to make the most sense right now, and it seems to be the most practical and the fastest way. Now, I agree 80% with that comment that pump and treat by itself will not restore aquifers to beneficial reuse. Modifications and optimizations to pump and treat have been evaluated and studied, and there have been successful optimized groundwater extraction techniques that have achieved MCLs for the contaminants at that time. Now, whether or not we'll be able to get to the whatever the MCLs may or may not be for these, it's important to remember that the how is a drinking water criteria. It's not a groundwater criteria. But whatever, wherever the toxicology falls, wherever the regulatory standards end up, if they ever end up for these compounds, there are ways to optimize groundwater extraction to make that work. There's not only different ways of pumping and re-injecting, but there's also various horizontal wells that can, through manipulating flow focusing techniques, can actually greatly improve the optimization of what would be a typical groundwater extraction treatment system. So I do think in the interim, point of use treatment is where we'll sit from immediately cutting off receptor pathways, but I do think there's some promise from a groundwater extraction approach.
And just on a related note, there are major public water supplies that, perhaps this is point of use, I'm not totally sure, that have put GAC onto the entire public water system versus private well GAC use. So where we've had sites that have had more of where a lot of people are on their own private drinking water wells, and perhaps the source of contamination is something aerial, kind of variable. In that case, we've applied the GAC at the true point of use, or as it's coming out of the tap, or right before it comes out of the tap. But there are some major public water systems that have added GAC on to treat at the public utility level.
Okay, let's take one last question from here.
Hi, I guess I didn't catch very much discussion about the use of UV. I know it was mentioned, it was listed in the presentation, and I was just wondering if there's been any significant studies on that and how effective that's proven with this.
Yeah. Go ahead, Eric, you can start.
So this is not an area of the literature that I'm super up to speed on. I know that the perfluoroalkyl carboxylates are capable of being destroyed through direct UV absorption. I'm not sure of the exact wavelength range. I think the sulfonates have been demonstrated to be still very recalcitrant to direct UV destruction. And unfortunately, a lot of what we're often dealing with is PFOS being a big driver of the need for treatment. Do you want to add to that, Jeff?
Yeah. So one way that we've been kind of capturing ultraviolet's use is through advanced reducing processes, because you can irradiate various species with UV and facilitate the generation of the aquated electron. For instance, sulfide irradiated by UV can facilitate that ARP pathway. So in generalities, talking about ARP, we kind of encompass UV, but there's been some pretty good work recently on different UV techniques, and we've actually piloted some field scale UV treatment at our site in Australia that Erika was talking about as a way to help accelerate destruction within the ozofractionation tanks. So I do think there's some viability to it, and a lot of municipal water treatment plants have moved away from chlorination-based disinfection and are using UV. So there might be some optimization there where you have an existing system and you're just changing the wavelength, which I want to say is the effective was VUV light, which was the 275 nanometer if I'm remembering correctly.
Okay, thank you, Erika and Jeff.
Thank you.
Thank you, guys. It was great to have the opportunity to present.
Yep, and if anyone is interested in more information about PFOS and PFAS or PFAS in general, and emerging contaminants, we are having an emerging contaminants conference on June 5th and 6th. And if you go to istc.illinois.edu/events, you can find out more information about that conference. Thanks.